Welcome everyone to another CP Tap call. This call number 162. I'm pleased to introduce Andreas Hillebrand, one of the broadcasting audio industry's leading voices on audio over IP, with more than 35 years of experience across software engineering, product management, broadcast systems, and industry standardizations. Andreas brings technical expertise and practical insight to one of today's most important production topics, synchronization in media over IP workflow. As a technology evangelist and senior product manager for Ravina at Lao, Andreas is actively involved in shaping the key standards and interoperability frameworks, including AES 67, SMPTE ST 2110, NMOS, VSF, and AIMS. In this session, he will explain how synchronization works in IP-based production environments, from audio-video, lip sync to sample accurate alignment across complex multi-stream workflow. So with no further ado, Andreas, the floor is yours.
Okay, thank you, Ahmed, for inviting me to this session.
Welcome.
And welcome everyone to this presentation on precision time requirements in media over IP, or as a more light title, why PTP is at the heart of your media over IP system. I hope everyone can see the screen by now.
Yes.
If not, okay, wonderful. So a couple of words, my person, thank you for introducing me. I have been working for more than 30 years now in the professional audio, particularly broadcasting industry. And I started off my professional career actually in the US, working for 2 years on real-time programming in industry area. The past 15 years, I've been working for Lavo on the Ravenna IP media networking technology, which has been designed from the ground up as matching the very strict requirements on professional audio broadcast applications. And those of you who are aware of the AES 67 and the SMPTE ST2110 standards, they had been published after Ravenna had been released. So naturally, they were based on the principles of Ravenna, so that Ravenna as a technology is fully AES 67 and 2110 compliant. And just a final word on the company I'm working for, it's Lavo in Rastatt. Lavo is a worldwide operating company, started out in the audio business, but is now one of the big names also in AV solutions for broadcast production. Headquarters is based in Rastatt in the southwest of Germany. And I'm here in Munich, enjoying the final sun rays which are coming through a couple of rain clouds which we had today. Let's set the scene. Let's open the curtain and welcome to the greatest stage which is currently going on. The greatest event, and everyone knows what I'm talking about. It's the FIFA World Cup, which is going on, and the main operations center is in Dallas, and I think it's Houston actually. Anyway, such an event typically has lots of venues, and if we just look at one venue, there's a lot of AV going around. A lot of pro AV applications include audio and video distribution, but also there's the special case of the broadcast production things. And as you can see from this image, there are a zillion of different areas where professionally produced broadcast signals are originating, need to be transported to, are processed and further distributed. And just to give you a couple of inside images, how this looks on the inside. We have a couple of images of audio production, graphics, video production, and also the main master control room, which is the lower part of the picture, where everything, audio and video, comes together, not just from one stadium, but from all stadiums. So every individual signal, camera signal, audio signal is actually ending up in the main operation center. And the whole technology behind that is in the central equipment room. And as you can see these days, this is a huge amount of servers nicely lined up one next to each other. And everything is actually transported, processed as data packets, as data flows on standard network infrastructure. So how do we transport real-time critical media signals, audio and video, and accompanying data across the network? Well, there are two fundamental approaches how media over IP can be transported. One is the bundled approach. That is a video and audio and metadata which belong together, originating from a camera and the adjacent microphone, for example, are transported as a bundled data stream. So we see audio, video, and metadata traveling in one packet flow, and the standard behind it is SMPTE ST 2022-6. So audio, video, metadata is a bundled stream with one IP address. Now, for production environment, like the master control room in the FIFA World Cup Championships, this is not a very suitable way to transport the signals, because if I want to process just as an individual essence, let's say the audio, for the audio mixing, I would have to unpack the individual essence, in this case the audio, from the bundled stream when it's transported as a ST 2022-6 signal. So we have a typically SDI video audio data signal, which is inserted into the network. And as an audio mixer, processor, console, whatever, I will have to receive the full stream, including the video signals, de-embed the audio, do the processing, embed the audio again, and send off another 2022-6 stream. So this is a lot of work and requires a lot of bandwidth. So that's why another standard has been defined, and that's ST 2110, SMPTE ST 2110, where audio, video, and metadata are transported across the network in separate packet flows or in separate streams. So in each streams receives, of course, its own IP address. So we have audio separated from video and metadata flowing around on the network. That is ideal for studio production workflows, because I do not have to receive the full media stream anymore. I can only pick the audio stream in our example where I do want to do the audio processing. So I pick just the smaller audio stream, do the processing, and reinsert an audio stream back to the network. So this is much less work. It requires less bandwidth on the network, and with the missing steps of the de-embedding and embedding, I also gain processing time, which means I can work with lower overall latencies in the production process. So that's a perfect approach for any sort of live production. And this is just summarized in this diagram. So we have 2022-6 as a combined or bundled media stream, which usually is applicable to program distribution, context exchange, long-haul contribution, some cases also for facility infrastructure. And then we have 2110, which is very suitable for distributing signals within the studio production environment, production compound. In this case, we have an example with the stadium, where all the signals run into an OB van, and from the OB van we can forward either 2022-6 bundled signals or also the individual signals to the broadcast studio. And in the example, or in the case of the FIFA World Championship, we have full SD2110 individual streams running from all stadiums all the way into the central broadcast compound where every individual stream is being processed. So, but in order to do that processing and relate material against each other, or to align things like, what video frame belongs to what audio block, we need time as a reference. And so time, the key part for time, or the core part for time, is in 2110 based on PTP timing. So that sets the scene, and now let's jump into how we use PTP and what requirements we have when it comes to time. So in professional broadcast, the general requirements are actually, we want to have full media bit transparency. So that means every single bit I'm inserting at the sender needs to be received and being processable, unchanged, full transparently at the receiver side. So audio-wise, we don't want to employ sample rate conversion, or video-wise, we don't want to employ, frame rate converter or something like that. And so the first requirement, which originates out of this, is that all the streams, all the sampling operations, everything need to run on the same media clock. Well, of course, audio and video have different media clocks, but when it comes down to audio, all the audio streams which I want to process have to run on the very same media clock. So all the devices need to be synchronized for that matter. Of course, originating from the fact that we're not just talking audio, but also distributing video signals, I want to have the possibility of concurrent operation of different media clocks on the same network. So audio video is distributed in the same network. Also, very critical for professional broadcast production is a determinable and low end-to-end latency, and a time alignment between the media streams. So I need to know which video frame belongs to which audio, because I want to have lip sync. Or if I'm receiving audio streams from the same sound field, let's say the stadium, where you have typically 10s, 12s, 15, or even more microphones positioned around the field, you need the time information in order to being able to relate the individual samples with respect to each other, to have a precise sound field reproduction when processing these signals. And of course, in legacy systems, legacy production environments, we had a so-called house clock or word clock, blackburst, whatever, running around the house, what we said, that's what we call house clock, but it actually is received by every individual participating camera, microphone, audio processor, whatever, and that was the reference signal for these devices. Of course, when we have a network in place, we don't want to run an extra house clock around. We want to have that on the network as well. So out of this, we can see that the typical clock reassembly from stream data, looking at individual incoming streams, is not applicable. We call this the asynchronous case. I will explain that in a minute. The distribution of master clock beats without a time reference is also not sufficient, because we can't align individual streams against each other. This is what we call synchronous operation. And we finally, at the end, need a common understanding of a reference time, which can be called wall clock, is called wall clock in some cases. And this is the full synchronous operation mode. That's what we want to have at the end. So what precision requirements exist? Well, if we look at audio and video, we all might tend to think, well, video has the most strong or most stringent requirements in terms of precision, because it's so much more data. Actually, when it comes to accuracy and precision demands, it's audio which has the toughest or highest precision demands, because what we want to be able to achieve is a sample accurate alignment of streams. So that means the maximum allowed deviation is plus minus half a sample between two streams. So we have a transmitter. Typically, if we have a media clock period, this is called a sample period. So this is one sample within the sample stream. And a receiver has its own, media clock synthesized from, I will explain in a minute from where and how. So if that slips like half a sample to the right, and another receiver which slips one sample to the left, we already have the maximum allowed amount, because in order to be within one sample, looking at both receivers, the allowed tolerance is maximum one sample period. But that means that each receiver on its own is only be allowed to have plus or minus half of the sample period with respect to the reference signal. Otherwise, I can't match sample accuracy between any two receivers. And that's what I definitely want to have. Otherwise, my signal slips. Only if it's a sample, it might not be that bad. But of course, our requirements are we want to definitely be sample accurate when aligning audio signals. And that translates into time requirements. At 48 kilohertz audio frequency or sample period, we cannot afford to have anything above plus minus 10 microsecond deviation. So that's the requirement at 48 kilohertz. And if we increase the sample rate in high-end production, we sometimes see 192 kilohertz. The stringent requirements, or the requirement goes up to plus minus 2.5 microsecond maximum allowed deviation in order to meet the sample accurate alignment. However, there's another requirement buried in the AES specifications. AES is the Audio Engineering Society that puts out specifications for audio processing. And one of them is the AES 11 specification for word clock reference stability and accuracy. And AES 11 says, okay, the maximum allowed jitter and wonder of a master or reference word clock is not allowed to exceed plus minus 5%. And that translates, well, here's just a quick explanation on that. So I have a word clock on the transmitter, and I have a word clock on the receiver. And if I want to stay within the plus minus 5%, this is the maximum allowed wonder and jitter. It's 0.05 of the whole clocking or sample period. So that is the mark which we need to match, and that translates into timing requirements. And the timing requirements at 48 kilohertz in this case is plus minus 1 microsecond. And if we do productions with 192 kilohertz, my maximum time accuracy, or the minimum time accuracy I need to match, is 250 nanoseconds. So the time at each participating device is not allowed to deviate more than 250 nanoseconds. So we need a clock distribution scheme, and there are several methods out there, and not going through each and all of these individually, but at the end it turns out that PTP is the protocol which would be able to fulfill those requirements. So with PTP version 1 or with the PTP version 2, which has been introduced in 2008, it is possible to have an accuracy of about 20 nanosecond. Of course, it can always get worse depending on network infrastructure and the way it's distributed. In some cases, you can even get better than 20 nanosecond, but the 20 nanosecond is an agreed number where people say, okay, that can be matched with PTP version 2, given that we have a proper network infrastructure in place. Just as a side remark, most often PTP is derived from GNSS signals, GPS or other references, and those satellite-based signals have an accuracy of 2 nanosecond or better, given that there's no spoofing or rogue hacking or whatever on the network. So PTP with a reference originating from GPS or GNS is what we were looking at, and that is actually the basis of all the media over IP production protocols or mechanisms or solutions which are deployed, or which have been standardized and are deployed these days. I don't think that I have to explain PTP protocol, so this is just a summary, a slide what it can actually do, and I definitely will skip the slides explaining how PTP works. If any one of you does actually not know how it works, there are a lot of good information on the internet, also on the Ravenna website, where we have webinars on this. They also explaining the latest edition, which have been added in version 2.1, which has been published in 2020. But I'm not explaining this right away. So I skipped the PDP explanation, and now I'm going to explain how the various clocking and synchronization models for media over IP work in general. So we have the standard RTP mechanism, which is part of the RFC 3550, being defined by the IETF. We have the Ravenna AS67 2110 and 702110 scheme. And there are also other mechanisms out there who work with PTP. But I'm not going to explain those because they are similar in principle with some variations, in the deeper technology. So AVB, TSN, and IPMX are other mechanisms which deal with sample accurate synchronization and media transport. I'm going to explain these two to see why we definitely end up with PTP and how that actually works. So we have RFC 3550, which is the generic RTP transport model, and the clocking actually works like this. We don't have a wall clock in place, but of course we have a sender and a receiver. Now the sender generates its own media clock or may take an externally provided media clock as the sampling instant. So in any case, the media signal is digitized to an AD converter, and a number of samples, depending on the chosen packet size, is being collected and then sent off across the network as an RTP stream. Now that RTP stream, as per definition of RFC 3550, has its own RTP clock that usually is directly related to the media clock. However, logically, it has its own timer on it. So in the case of linear PCM audio, it's nothing more than a media clock counter, actually. However, it's important to understand that the media clock counter has a random offset with respect to the underlying media clock or generating media clock. The reason for a random offset between any two streams is that the folks who invented or standardized RFC 3550 were already concerned about security. And so they said, okay, the way we transport the information is part of the encrypted part of secured RTP, SRTP. And so in order to not have a hook for a crypto attack, we cannot have a known value inside the encrypted data section, and that is why we want to apply a random offset to each individual stream, which would make it not as easy to have a hook for a crypto attack. However, the offset, of course, is constant through the stream's lifetime, and it's transported out of band through the SDP file, which is also part of this RTP transport scheme. The receiver is now receiving the data packets. It will store it in a jitter and delay buffer. It usually has a configurable delay, but it does not yet know the precise media clock. So what it has to do is actually it has to recreate the media clock through an adaptive algorithm observing the receive buffer fill level. So it can assume, the sender is sending at 48 kilohertz, so it may start its media clock at 48 kilohertz, which is not the same 48 kilohertz actually as the sender, because there's no common reference there, right? So it starts at 48 kilohertz, and if that clock is faster than that one of the sender, it observes that the buffer fill level decreases, so it's running too fast, so it will slow down its media clock until it observes that the buffer is filling up again. If it's filling up more and more and more, it will slow down the media clock for taking out the samples of the buffer and playing out the media. So that is how the receiver recreates the media clock of the sender with, depending on the quality of this, this algorithm, of this observing algorithm, depending on that, the media clock is not completely stable over time, but it can be quite good depending, how long it takes for this algorithm to settle, uh, on the, observing algorithm of the incoming data. So this is more like an implementer's choice, but this is how a receiver without any, reference to a wall clock can resemble the incoming stream data. This is all covered by RFC 3550, the original RTP stream, and there are some benefits and drawbacks. The benefit, of course, is any input signal with any media clock can be transported and reasonably well be reassembled, and that all depends on the quality of the sender-receiver clock circuitry, as I just explained. However, without SRC, there is no concurrent processing of independent streams. So that means if I, from one single receiver, receive two independent RFC streams, RTP streams, according to RFC 3550, they are not related clockwise to each other. They are about the same 48 kilohertz, but not exactly. So one might run a bit faster than the other. And in order to produce, like if I want to mix them, for example, in order to produce a constant aligned flow, one of those streams at least would have to run through a sample rate conversion in order, to have the same playout media clock for both, or actually any incoming stream. So, but with SRC, we don't have bit transparency anymore because the bits are altered, actually. Also, since there is no notion of time reference, I don't have the ability to align the content of two individual streams against each other because there is just no deterministic latency and no reference to the originating time. In professional environment, because of this, deviating media clocks once I generate them independently locally, you often have this house clock running around. So the house clock is sort of a reference. And this works like, here's our example again from the RTP case. And now I feed a reference clock to all participating devices. In this case, the sender and the receiver. So I have a reference clock, and that's really a clock, a media clock, that is being fed to the sender and the receiver. So I now have the same clock on both devices. And that means in turn, well, my stream data follows the media clock. The receiver gets the stream data. It has the same media clock. And so that means I can decrease the size of the buffer, which translates into latency, of course, because I now know, well, there is no buffer going up and going down and adjustment requirement anymore because I consume the data. I consume the data from the buffer with the very same speed I'm getting data into the buffer. I only need to take care about network jitter and the packetization itself, so that I never run out of data because the next packet hasn't yet arrived. So that's certainly a big advantage. Sample rate conversion is out of the game. Same media clock for all streams. It's possible to concurrently process these streams. However, I still don't have any time alignment on that. And with that, I don't have a deterministic latency. So I don't know if one stream was traveling across the network, let's say for 2 milliseconds, and the other one maybe for 3 milliseconds or 4 milliseconds. I only know once I am receiving the streams, they are locked to each other. But I don't know actually how they actually relate with respect to the source, to the originating time. Now, that is what AES-67, so Ravenna 2110, have taken into account. And so the way synchronization and media clocks work in Ravenna AES-67 is like this. So all nodes still need their local clocks. So they are running local clocks which are generating the media clocks finally. The local clocks are now precisely synchronized to the common wall clock via the PTP protocol. And from those local clocks, I can generate any desired media clock which in case of 48 kilohertz is now exactly the same 48 kilohertz on each and every device, because they all receive the same time. They all follow the time reference. So if I have the same time in every device, if it's only precise enough, then I can generate the very same nominal frequency independently, but fully synchronized in each individual device. So that's quite easy diagram. I have a master clock in the system that might be a reference to GPS or not. I have my slave clocks, which are the devices, the device internal clocks. And these are synchronized through PTP, so they all have the very same time, down to the necessary precision and accuracy, of course. And once I have time in individual devices, which is the same everywhere in the system, I can generate any desired media clock. And if I generate two nominally identical media clocks, they are also physically identical, because they are following the same time. Frequency is time at the end, very easy. So I now have identical media clocks at each participating device. That has the advantage that because I'm now distributing time and not a clock reference, that I can run any desired media clock on the network, and the concurrent operation of different media clocks is possible. Of course, an audio device which is set to, let's say, 48 kilohertz cannot at the very same time receive an audio stream of 96 kilohertz, or unless it has multiple media clock generators inside, which is an implementation specific detail and is not depending on the technology as well. If the PTP distribution is accurate enough, I can also match the requirements of AES-11, which is this plus minus 5% deviation. And if I have cross-facility stream distribution, I can also achieve a precise synchronization by using GPS or GNSS references individual at each location. So I don't have to transport or distribute time via the PTP protocol across a wide area network connection. I can rely on local GPS or GNSS referenced grandmasters. And now the trick is that once I have time and have the identical media clocks, I can apply the sampling time to the digitized essence. So in other words, each audio sample or each video frame receives the accurate time of its generation or sampling into the camera or the microphone. So, and to get a bit more into the details, there are three types of clocks in each system. That's the wall clock provided by the grandmaster, which lives as a local copy in each individual node. We have the media clock, which is derived from the local clock, but it can be any desired media clock. So 48 kilohertz typically for audio, 90 kilohertz for video. And we have the stream clock, the RTP clock, because what we employ is still RTP following RFC 3550. And this looks better in the diagram, of course. So we have the reference clock that with the grandmaster. We have the local clocks, which are synchronized to PTP. The media clocks are directly derived from the local clock. And of course, that's the very same thing in every participating device here in the receiver device. I generate the stream data following the media clock. I still have the random offset as being defined by RFC 3550, the RTP standard. And this offset, as already described with 3550, it's actually 4566, is conveyed in the SDP file, which basically describes everything I need to know about a particular RTP stream, like stream format, like payload format, and so on, so that the receiver at the end knows what is the content of any particular stream it actually receives, and what's the relationship with respect to time. So the receiver gets the SDP file, and it's already running the same media clock, and through the SDP file, it gets the information if the timestamp, or what the timestamp of any individual sample is with respect to the sampling time on the sender side. So it has an exact understanding of the frequency and the origin timestamp. When it comes to ST2110, there's a constraint. They were discussing that they think that the random offset, which was originally in place for defeating crypto attack, is not something they want to keep or want to feel very important for the closed production environments 2110 is typically running in. So they constrained that the random offset has to be 0. Don't want to go into the discussion of this, but it's just one of the constraints in 2110. But basically, it doesn't mean that there's any interoperability issue because that offset, in any case, will be conveyed and signaled through SDP anyway. So how does that translate into an RTP packet? We're still talking RTP 3550. So we have an RTP packet which consists of a header and the payload area. So we have the header and the payload area here. And in the header, there's a field called timestamp. And this is basically a media clock counter. When it comes to linear PCM audio, it's also a frame counter when it comes to video. So it's basically counting the media clock periods. And whenever it has a sample, it puts the media clock counter value of that first sample in the data area into the timestamp. So typically you have like 48 samples with one packet. At least that's the mandatory interoperability point with AES67. So the timestamp in the RTP packet tells you, okay, the first sample in the payload has been generated at the sender side at this particular media clock counter. And of course, within the standard, all the media clocks are back referenced to one common origination time point, and that is the TAI domain. So it's the 1st of January 1970. From there on, the media clock is being counted, and that is easy math at the end. However, of course, it's a 32-bit field, so we have a rollover roughly once per day. But hey, we are talking live production, so it's very, very unlikely that a stream is on its transport way for more than a day, unless I'm transporting something to Neptune and back. And so this is not a problem because we are talking about, milliseconds or maybe even just seconds. So it's always clear when a particular sample had been generated, taking the time of day into account as well. So, and now the fixed and determinable latency can be set or can be calculated by using a suitable link offset or playout delay. So how does that work? Let's have a quick look at another diagram again. We have the sender with its sender network system. We have the ADC, the converter, the sender packet buffer, the media clock generation, and then we have a network stack and controller, whatever it's required. We have the same thing on the receiver. It only has the DAC, so the output stage, and it has a slightly larger receiver packet buffer or receiver sample buffer. Now, just for informational purposes, we also have the IP network and the 1588, the PTP measurement planes. Those measurement planes are working on the point where data is handed over from the NIC to the PHY or from the PHY to the network, depends on the implementation. This is just for the synchronization of the clock. But it's not the plane where we measure or where we have the origin point in time for the audio samples. That is called the ingress time reference point and the egress time reference point. And that is at the point in the sender architecture where a sample is actually being acquired or where a particular sample is destined to being played out to leave the receiver network system and is being forwarded to the digital analog converter in any subsequent processing stage. And the time between this is called the link offset. So now, since I know the exact point in time when a particular sample is being ingressed, of course, it's, it waits for other samples in the sender packet buffer. It's handed down to the network stack. It's put on the network. It travels to the network. It is being received. And there is jitter on the network, there are processing delays, and so on. But at any point in time, it still carries its origin timestamp, so the media clock counter. And once it is in the receiver packet buffer, there will be most likely 1 or 2 complete packets. So let's say 50, 60 samples being stored in that packet buffer in order to cope with any of the potential jitter in the network. But since I'm running the same reference time, the same media clocks, I can set an appropriate link offset, let's say +3 milliseconds, +5 milliseconds or something like that. Or depending on the network and the packet size I'm choosing, I can also go down into like, just 10 samples or 5 samples of link offset. And then the receiver exactly knows when to forward a particular sample from its receiver buffer to the processing stage. And this is a determinable fixed latency. And the math behind that is we take the RTP timestamp of the first sample in the packet, we add the desired link offset, let's say +3 millisecond in the example I just made. We have to subtract the random RTP offset. Remember the RTP offset, which is random for each individual stream. It could be 0. In most cases, it will be 0 following ST2110 specifications. And then I have calculated the desired playout time for the sample, and everything the receiver needs to do is, pick the particular sample and forward it only to the output stage when its playout time has been reached. In practical, it's even more simple and easier than the theoretical math behind this explains, but this is to understand how this works so that we achieve a determinable and fixed delay or latency across the network, and that can be calculated individual for each stream. So it's not a network-wide or system-wide latency. It's not a device-wide latency setting. It can be individually set for any individual stream. And that's the way how we can actually cope with, let's say, latency differences for a live application where we have a PA system where one set of speakers is in front of the stage, another set of speakers is more toward the audience, and of course we have acoustical delays, and that means that we can delay the playout of those speakers which are closer to the audience by several milliseconds, so that the playout of the samples from the speakers aligned with the stage has time to travel, and once they reach the plane where the other speakers are sitting, those speakers play out the related samples, and so we have no mix and match of samples not belonging to each other, just as a quick example here. And since we are sample accurate and can be even subsample accurate with the phase accurate alignment, projects like the Sphere in Las Vegas, which most of you, I believe, know and hope you have the chance to see a performance there. That is very, very impressive because we have an array of 1,600 individual speaker devices with 100 individual powered speakers, receiving up to 256 channel streams, any number of streams actually on the network, and they are all played out as they do wave field synthesis and beam forming. They need to have a precision which is subsample accurate, and this is all done actually with a Ravenna system based on PTP. So very impressive and this principle, which underlies AS67 and SMT2110 as well, can actually achieve. Okay, so last step is basically, I already explained this, the inter-stream alignment can be done by comparing and relating the timestamp to of the individual essence data. So the example I just made, so delay the playout of speakers which might be closer to the audience, or like, delay the playout of audio in order to reach lip sync alignment on a particular display with their associated speakers. Okay, so the main benefits and also drawbacks of the asynchronization scheme are all media clocks are now following a common reference. That means I have an accurate reproduction of the reference clock on all nodes and identical or even phase accurate media clocks for all streams. That means I can concurrently process any individual independent streams because they are all related to the same reference. I have a complete deterministic latency, and a sample accurate alignment of streams is definitely possible. It's actually a subsample accurate alignment, which is made possible with that. However, I lose the ability to transport asynchronous input signals. So if I have, free running audio signals, or audio video signals, like typically on a free running HDMI sender, which might not be synchronized to anything, I can ingest that into an AES67 or 2110 sender, but I definitely have to sample rate convert or frame rate convert that signal in order to match the overall system reference. So I definitely lose the ability to transport asynchronous signal with Ravenna AES67 or 2110. I always have to sample rate convert that to the system time reference. Now, since we are talking PTP, we know that PTP comes with profiles, and AES67 and 2110 have been defined by separate standardization organizations, where AES67 had been defined in 2013. SMPTE has been defined in 2017. Well, that's the publishing dates. Of course, the work started a couple of years earlier on each respective standard. And Ravenna had been released in 2010, and we started working on Ravenna in 2008, actually. And with PTP, at the beginning, the only meaningful profile we had in the case of Ravenna was the default profile. So we put forth the requirement that every Ravenna device needs to be able to work on a PTP default profile. And when AES67 looked at PTP, they said, okay, PTP default profile, it's quite difficult to achieve precision because you need to implement very, very precise and accurate and sophisticated clocking circuitries. They might be expensive, actually. And so in order to ease the implementation a little bit, they defined the PTP media profile, which comes basically with slightly changed recommendations or definitions for sync rate, announce rate, so that devices do see more sync rates per second or have more announce messages per second, so they can settle faster to the desired frequency or to the desired time, actually, and can generate a stable frequency with less effort in the circuitry itself because it sees more frequent synchronization messages. And then SMPTE came up with even more stringent or constrained profile, which is called the SMPTE 2059 PTP profile. So the AES67 media profile is normative, but it's an optional. We have additional requirements I don't want to mention here in detail. And that's the overview of the important, or the more important, the most important message range. As you can see, the announce interval default is 2 seconds, which matches the PTP default profile. But we also have sync intervals, which go down to 1 to 16 sync messages per second, with the default interval of 8 sync messages per second. However, the range is covering the default profile as well. So the default PTP profile lives within that particular media profile, but the media profile says, okay, you can work at higher sync rates, for example, or higher announce rates. And 2059 basically does the very same thing, but improves or extends that range even more. You can see the sync interval can go down to 128th of a second. And they put forth the maximum sync interval to 2 sync messages per second. And just picking the announce interval for now, the default announce interval in 2059 is 4 announce messages per second versus, an announce message every 2 seconds in AES67 media profile. And then we also have the default profile. And then AES sat together and said, okay, what can we look at the different profiles we have for media applications? Default profile, the PTP media profile, AES67 set forth, and the 2059 definition. Is there a common operating point? Because we don't want to have 2 different clock domains. on the network just to operate AES-67 and 2059 concurrently on the same network. So, and then they worked through all the profile settings. They summarized their findings, the differences and commonalities in a freely accessible report, ASR16, published in 2016. And that report also includes recommendation for settings when operating AES-67 and 2110 devices on the same network. And luckily enough, for each and every definition of a parameter rate or parameter interval, there is an overlap. And just taking the announce rate into as an example here did not match the other values here. It's just the default announce interval. AES-67 says, okay, if you're operating at 1 second per one announced message per second, you are good with all devices because all devices are supporting this. Okay, so, and then finally, I had some deployment tips in here, but this is more like for project-oriented people. Let's continue with one important thing, which yet needs to be solved, actually. I told you that inter-stream alignment is possible, by comparing and relating the timestamps of the individual packets with respect to each other. Well, that is true if I have one sender and one receiver. Well, what happens in a typical production workflow? The typical production workflow on the video side might have a camera, might have a number of processing devices, and might have a display at the end. Now, the link offset I described is only valid between two individual or two participating devices. So since I am not aware of the processing time in the AES-67 or 2110 scheme, I have a sequence of different link times. So at the end, the stream which receives at the display has an RTP timestamp, but that only refers to this senders, to the last processing device timestamp. And it has no reference to the origination timestamp. And if I take audio into the game as well, there might be just a mixer in between. So we have a microphone, but I again lose the original reference or the original alignment, because there's the processing stage in between, which sends out a new RTP stream. So the speaker actually, or at the speaker, I just don't know what was the originating time from the microphone or at the microphone. And okay, this has been, of course, identified, but it's not covered with Ravenna AES-67 or 2110, its core specification. I'm just bringing in the buffers here because these are part of actually all the devices. So at the end, to align the audio stream with the video stream, because that takes more time apparently over here, I need a much larger buffer at the speaker in order to align the streams originating here, but I don't have the actual alignment information anymore because I lose this basically because it's only the stream alignment, this individual stream alignments. So the question actually is, how do I synchronize the streams across various processing stages? And the problem, as I described, is the streams are only leaving as a new stream per device. There's a new alignment of the essence, and the original essence alignment is definitely lost. So possible solutions. The guys in the SEMTI group suggested, okay, why don't we use the original RTP timestamp, which the receiver sees, and putting it on the packet which contains the processed sample of that particular. So reusing the original RTP timestamps. Well, this is not how 3550 has defined this, because 3550 has defined the RTP timestamps as being, whatever is being created at a sender, this is the point in time when it has been created. So it's a transport timestamp and not a original essence metadata timestamp. Also, by using the scheme, the offset increases, of course. It might get too large for a downstream receive buffer. Also, then, when mixing two incoming streams, what is the actual referencing timestamp? Because that takes more time, apparently, over here. I need a much larger buffer at the speaker in order to align the stream timestamps I would have to use. And then also the processing device itself may not know the exact relationship between ingress and egress. In some cases, it might not even be possible to put to adjust the output packets the very same manner the input packets have been received from the network, because the processing, moves the boundaries of the packet blocks. So that is apparently not really a good solution. It could work or can work in some cases, but it's not a very general solution. Now, we can also carry the origin timestamps as in-band metadata. Because the original timestamp is a metadata, I can try to carry those in-band. Now, carrying timestamps, additional timestamps, in addition to the RTP timestamps in-band, means I have to define a new payload format, because none of this is existing at the moment. Or I can make use of the RTP header extension mechanism, which still is in an experimental RFC. However, the downside of this is, if I'm using header extensions, I decrease the audio payload or the media payload segment. And if I put more information into the RTP header, because once it's there, there's also a desire to put even more metadata information into that. And that might even turn or result in variable payload segments, which makes it even more difficult to calculate with the overall throughput and the necessary required latencies and bandwidth and so on. So that is also not a very good idea. So what about carrying the origin timestamps as out-of-band metadata, what it actually is? Well, that would require a new standard in order to let every device within a system settle on the same mechanism which is actually used. And luckily enough, there are some organizational bodies which are working currently on that kind of mechanism. The AES is, well, it currently has stalled work on this or paused work on this. SEMTI is working on this. It could be a new NMOS specification, which is also part of a larger broadcast infrastructure. So a new standard certainly would be required for that, to let all the devices work on the very same mechanism. So at current, we basically only have one solution. We leave the alignment task to a management layer, an orchestrator or broadcast controller, or even a human being. So what we need to know is basically the device's processing delays to the broadcast controller, or they have a fixed or configurable delays, depends. And the broadcast controller then calculates the required RX, or receive delays, for all the subsequent stages in a playout chain. In terms of the diagram, this would look like this. We have the link time, which is being reported or set by the broadcast controller anyway. The devices now report their processing times, the individual processing time. So the broadcast controller exactly knows how long a particular sample or frame is inside the processing unit before it's being put back as a packet on the network. The link times are set by the broadcast controller anyway, and that now gives the benefit that I have the chance to not put the whole burden of aligning the final output through a very large delay on the, let's say, on the speaker buffer, but I can distribute parts of this already here on this input buffer, because what counts at the end is only the overall delay. So I can evenly distribute the necessary or desired playout delay in a particular chain of processing devices evenly among participating devices. That's one of the benefits of that. However, this is in standardization at the moment. So right now, if you want to achieve, for let's say, lip sync between a video signal, which is passing through different processing stages, and the related audio signal, which is also passing individually through processing stages, you will have to do a manual adjust on the output side or in the in-between stages to achieve the perfect alignment. Unfortunately, that's the way it is by now. So that basically concludes the presentation on how Synchronization is achieved within media production systems, audio, video, and what important role PDPs actually plays in that process and why it's been PDP and nothing else. If there are any questions, I'm happy to take them.
Great, thank you very much. Yeah, let's open the floor for questions.
I have two questions, Ahmed.
Go for it.
Good. My first question is related to slide 41. Slide
To what?
41. 41. Slide 41.
Slide 41. Let me see.
It has number 41 at the bottom.
Okay. Yeah, try to get it. 41.
And you have
41.
this S parameter.
This one?
Yes. The S parameter you mentioned here. I really missed it. I don't understand how you calculated it, what it does.
Yeah. So basically that goes back not to this slide, but it goes back to the slide before. So the original RTP scheme, right? It's already in here. So the way the stream data is transported with RTP is with PCM audio, so linear audio, is sample-wise. So that means samples relate to each period of the media clock. So at each, let's say, rising edge of a media clock, there is a new data being sampled, either through the AD stage or just taken in from the input stage. That is stored in the input buffer. And I need a number of samples which are collected in the input buffer before I can generate a packet and send the packet on a network. Now, the timestamp is mentioned in this particular slide. So that timestamp of the first sample in this packet is not a timestamp, it's the media clock counter. So imagine the media clock starts at the 1st January of 1970, because that's how we define the media clock counter to operate in AS67. So media clock virtually started 55 years ago at a defined point in time, the origin of TAI actually. So, and you can exactly calculate when you start up a device, what is the media clock counter I am working on right now? And from there on, the media clock counter increases. So the timestamp you see in packets is basically, if you have 48 samples in the packet, let's say you have a timestamp of 100, which is marking the 100th clock cycle, which relates to the first sample. The next packet will show 148 because it's 48 clock periods passed, and the next sample the first sample in the next packet is 48 samples later. So now, if every individual stream on the network would have the same timestamp, you could relate by looking at the RTP. With encryption, when encryption comes into game, this is all part of the encrypted data area. So, however, since I have a clue by about knowing when a particular sample has been generated, because I know its reference to the TAI, and looking at two individual streams, it would make the attack much easier because I have a known value. And that is the reason why the IATF guys who defined the RFC have said, okay, you can counter this by applying a random offset to the timestamp, to the media clock counter for each individual stream. So you have no correlation when looking at the encrypted data, how this relates to each other. Don't ask me any cryptographic details here, but that is the main reason why we have a random offset applied to the media clock value, to the timestamp value in the RTP packets. That is something which is not special for Ravenna or AES67. This originates fully from the RTP RFC 3550 definition. You can look that up there, and then they would explain exactly why they are doing this.
Okay, thank you.
So the receiver actually, and to just complete this, the receiver needs to know this random offset, because if it doesn't know the random offset, it has no chance to correlate two individual streams sampled accurately against each other, because there's an offset, and how should the receiver know? So that's
Yeah,
why the
right.
offset is
Yeah.
communicated
So,
out of band.
yeah, yeah, exactly. I can go back to the RTB, RFCs for this. Okay, good.
Yeah.
A second question is related to which protocols handle this actual session setup and management. Like you talk about SCDP, which
SDP.
SCDP, session description protocol, right?
Yeah,
Which
it's SDP. That's
yeah,
RFC 4566.
yeah, exactly. And this conveys clock offset parameters, but you didn't talk about the discovery and connection management
Oh, okay. Yeah,
protocol,
yeah, yeah.
not
Yeah,
like
because that
SAP,
is,
like
okay,
SAP.
that is, yeah, good, got you. Of course, it's a good question to understand the fully operational system, but this is not part of the synchronization and
Exactly.
timing.
Yes, you're right. I got it now. Yes, because
The
somebody,
discovery, yeah, go ahead.
somebody, Ahmed invited Steve from Meinberg, and
Yes,
he talked about NMOS IS
yes,
04/IS
yes,
05, and
yes.
there is, of course, SIB, which is very well known for session setup and management. But now
Yeah.
I got it.
So,
You only focus on time
yes,
synchronization. Yes, yes,
yes.
I got it.
Just to make a comment on that one, when we started with Ravenna, we developed a fully layered approach. So we were
Yeah,
defining the timing and synchronization, the media clock generation. We were defining what protocol to use to transport. We're defining how the description of a transport stream, and always using standards in this case, right?
yeah,
SDP is not for that. And then also, how is the multicasting done on the network? How is the
yeah,
unicasting done? Of course, they are all proven mechanism, and we stick to those mechanisms. And then you need to know, okay, in particular, when you want to receive a multicast stream, where can I receive that particular stream? So you need to have the multicast address. And then you also need to know what streams are on the network. So it's discovery mechanism. So, and through discovery, in which case we use DNSSD at our first, definition within Ravenna, you get an URI where you can access the SDP file. How do you access the SDP? Well, we have chosen RTSP protocol because that works for
yes,
unicast and multicast. And through the RTSP protocol, you get the SDP. In the SDP, there's the multicast address, but there's also the stream description, including the time reference and the offset parameter. And so we have a layered approach with Ravenna, and that gives us the benefit of easily adding NMOS, because NMOS is taking care of the discovery and the connection management.
yes,
It does the
yes,
very same things, and it doesn't change the mechanism, how the synchronization of the transport works.
exactly. So I think between you and Steve presentation, we can have a complete picture. I get it now. Thank you very
Yeah,
much. Thank you.
absolutely, absolutely welcome. Any more questions?
All right.
Yeah, if not,
If none, then yeah, we can conclude for anyone. I don't think anyone. Yeah. So if none, so we can conclude today's session. Again, thank you very much, Andreas, for this.
final word. I wanna encourage you to, if you wanna dive a bit deeper or are curious about anything I've said, you will find presentations on timing synchronization, but also on the discovery and connection management, and even on other topics related to media over IP. On the Ravenna network side, and it's not only covering Ravenna because AS67 2110, the inherent genes of Ravenna anyway. You will find anything you need to know in the resources section, which has also not just white papers for downloading, for free download. It also has lots of webinar recordings plus the slides. So if you're curious and want to dive deeper into anything, I can only encourage you to go to the Ravenna network site and digest the resources. Or shoot me an email at info@ravenna-network.com.
Yeah. What is your email address?
Yeah, you can use the info@ravenna-network.com.
Okay. Okay.
Excellent. All right. So again, thank you very much, Andreas, for this informative presentation. And we'll see everyone in 2 weeks by a presentation from Lian-Min Wang, about PTP for SDN, a low jitter PTP clock provisioning service via software cross timestamping. All right. Bye, everyone.
Thank you very much.
So thank you everyone for having me, and
Goodbye.
good night.
Very well. Bye.